My name is Pooja, and today we are going to discuss problem 1 from lab 2B or from discussion section 2B. Okay, so this lab is about product construction of DFAs. So what do we mean by product construction? Let's go through that quickly before we get actually to the problem. So why would anyone even concern themselves with something like this, right? Why would people think of doing a product construction? So suppose you have two languages, let's call them L1 and L2, and you have a DFA which we will call as A for accepting L1, and you have another DFA, let's call this DFA B for accepting L2. And now I ask you that, okay, create a DFA that accepts L1 and L2, or something more complicated, L1 XOR L2, or even let's say L1 bar XOR L2. Okay, so if I give you questions like this, then with the knowledge of DFAs for L1 and L2 separately, our question is, does it make creating a DFA for this easier? And the answer is yes. Using product construction, it does make it easier. So first of all, let's understand intuitively why this should happen. So we want to accept all strings W. Let's just look at L1 and L2. So we want to accept all strings W that are in both L1 and in L2, right? So what is an obvious way to do this? An obvious way would be run L1 on W, okay? Then we run L2 on W, and finally accept if both accept, otherwise reject, right? Else reject. So yeah, cool, very good way. And we would have liked it if this worked, but this does not work. Why do you think it would not work? I would suggest you take like 20 seconds to think of this on your own, and pause the video over here, and then come back. Okay, so this does not work because DFAs. How do DFAs work? A DFA has this uh, has a DFA is this machine over here. Okay, it has access to this input string, and it can read this input string only once from left to right. Okay, so if there's 1 0 1 1 whatever up to this, it is going to make one sweep of this input string, and that is all it gets. There are no do-overs, there is no going back. DFA is a memoryless structure, it is a memoryless machine. So the problem with running this sequentially is, once you run L1 on W, you lost your input, right? You no longer have access to W. So run L2 on W cannot happen because there is no W anymore in our hands. So to get over this problem, what we would want to do is, we would want a parallel computation. Parallel computation of these steps 1 and 2. Okay, so this parallel computation is exactly what product construction is. So to make it a little bit more formal, let's have the DFA's A as sigma QA start state of A. So this is all this is the set of all states of A. This is the start state of A. Then we have a transition function for A, and finally we have the accept states of A. Okay, let's just call this DFA D1 because the A is becoming overloaded, and I will just have ones over here. Okay, so this is our first DFA, and similarly we have DFA D2, which has the same sigma, a different set of states, a different start state, a transition function, and a set of accept states from here. So now we want to run these two things parallelly, these two DFAs. So the product DFA, let's call this D, would have same set of alphabets. So the set of so it would have the same set of alphabets. The set of states over here, let's call this Q. So this is now going to be a tuple, Q1 comma. So it is going to be all states Q1, Q2 such that Q1 belong to Q1 and Q2 belong to Q2. Okay. Then we have start state S. Now, so because the set of states is a set of tuples, so the start state has to be a member of this queue, right? So the start state is also going to be a tuple. And because we are running parallelly the original machines, the DFAs D1 and D2, that is why our start state reflecting that is going to start in this state, S1, S2. So it starts the DFA D1 in S1 and it starts the DFA D2 in S2, and it is going to parallelly run on it. So we have Q, we have S, then we have transition function delta. So how is delta going to look? So now delta is always from Q cross sigma to Q. It looks at a state, it looks at the input alphabet, and it changes its state. So now the Q, the set of states, is a tuple. So it will be from Q1 comma Q2 on an input A. So delta of this would be what? So what do you think it should be? So we want, what do you want our DFA D to model? We want it to model the running of D1 and D2 on an input string. So this is just going to say that, okay, I am seeing A over here. So for my D1 part of the D1 part of me is going to run the D1 automata. So it is going to use the transition function from D1 delta 1, and it is going to use the input alphabet on the state of that thing. And for the D2 part of me is going to run D2. So delta 2 Q2 comma A for all A in sigma, and for all Q1 Q2 in Q, which is Q1 cross Q2. Okay, so that is our transition function delta, this. Okay, and finally, we want to define the accept states. Now, depending on what product we are modeling, the accept state changes. Okay, so because suppose I want to model L1 and L2. Okay, so I want to accept if both of them accepted, right? So this DFA is like, okay, if I am in a state in which, so now this DFA has run W on L1 and W on L2 parallelly, okay, using this delta transition function. So now this DFA is saying that, okay, if the L1 part of me is accepting and the L2 part of me is accepting, then I will accept. So how does it say this? It says that, okay, it is all states Q1 comma Q2 such that Q1 belongs to A1 and Q2 belongs to A2, right? So this is how we model product construction. Now, if you wanted some other thing, suppose you wanted L1 or L2, then only the accept state changes. Most of this general boilerplate of sigma Q S delta remains the same. If it is L1 or L2, then this becomes OR. If it is XOR, this becomes XOR, etc., etc. Okay, so that is how product construction works. Okay, I think we have all the theory we require to jump into the problem now. So let's see what our first question is. We want to describe a DFA that accepts this language over 0, 1. Okay, so whenever you are faced with a question, just highlight all parts that are giving you information. Okay, so what all do we get here? We get sigma is 0, 1. We need there's this and over here. Then what are the two DFAs that are going to be that we are going to add? There is all strings in which number of zeros is even, and all strings in which number of the ones is not divisible by 3. Okay, so let's write it. So now we are going to be looking at problem 1 focused. Okay, so we need two DFAs. One is number of zeros is divisible by 2. Oops, this divisible. And the second is number of ones is not divisible by 3. Okay. Okay, let's double check the question. Number of ones is not divisible by 3. Number of zeros is even. So that means number of zeros is divisible by 2. Yeah, so we have the question down and these two are going to be in and we already know how to write the product DFA using this part of our thing. So okay, let's dive into this. So let's describe a DFA for this. This is going to be our DFA D1. This is going to be our DFA D2. We know how to write D1 and D2 using this. So how will DFA D1 look like? So first of all, sigma is 0 comma. Let's write the obvious things. Then we want to define. So whenever we want to describe a DFA, we need what? We need sigma, we need the set of states, we need the start state, the transition function, and the set of except states. Okay. So one by one, we are going to fill this information about both the DFAs. Okay, so we have filled sigma. What is the set of states? So set of states for a DFA should always reflect what the problem is demanding. So what is the problem? What is the problem demanding over here? We want to count the number of whether or not the number of zeros is divisible by 2. So our problem demands us to keep a track of parity of the number of zeros we have seen till now. And what possible parities could there be? It could either be odd, so number of zeros mod 2 is 0, or it could be even. So number of zeros mod 2 is 1, right? So these are the only two states. So we'll be trying with just these two states. So in more complicated questions, you might think of some set of states and then they might turn out to be wrong and then you have to reiterate and change some things over here. But okay, let's see if we have to do all these things now. I hope not, but yeah. Okay, so the start state. So now start state is going to be one of these two states, right? And when we start, we have seen nothing. We have done nothing. So the parity, the number of zeros is 0 up till now, which we'll say is divisible by 2. So we start in 0 state. Then we need the transition function delta. Okay, so if this was called Q, then when I'm in state Q and I see a 0, okay, what am I going to do? So for this DFA, let me write it. Let me just write it all and then we will write it succinctly later. So if I am in state 0 and I see a 0, okay, then the parity of number of zeros has changed. If I had seen even number of zeros until now and I see another 0, then I'm going to see odd number of zeros, right? So I have to change to 1. If I am in 1 and I see a 0, again, the number of zeros up till now were odd. I saw a 0, so now the number of zeros is going to be even. So that is reflected by 0. So let me just write it over here in small letters. This is even and this is odd. Okay. Similarly, if I was in odd, in even, the number of zeros were even, and I saw a 1. Okay. So having a 1 does not change the parity for number of zeros. So I remain in this state. If I was in 1 and I saw a 1, so I was in 1, that means the number of zeros is 1 more 2, which is odd, but seeing a 1 does not change it. So I remain over here. Okay, so how do we write this in a slightly more succinct manner is, we will denote this variable by Q, the state variable, and we say delta of Q on 0 on any alphabet A, in fact, okay, on an alphabet, let's say R, to keep the notation in the solution sets and the same. Okay, I think the notation is, okay, so let's say the delta of Q on 0 is going to be Okay, so we are in Q and we see a 0. So this is going to be, so the number of zeros increases by 1 and it is going to be modulo 2, right? And delta of Q on 1. So Q is now kind of representing the number of zeros, but except it is not representing the number of zeros, it is representing number of zeros modulo 2. And so we maintain that over here. Delta of Q on 1, it just is same as Q mod 2. But since Q mod 2 itself is Q, so this is just Q. Okay. And so this becomes our transition function. And finally, our accept state. So we accept when the number of zeros is divisible by 2. So our accept state is just 0. Remember to put the braces on because the set of accept state is a set of states, not a single state. Okay. Let's see now. D2. Now we want number of ones is not divisible by 3. So again, let's write the obvious. We again have to give these 5 elements. So sigma is 0, 1. This is true. Q. Now, what do we want to keep a track of? We want to keep how many number of ones modulo 3 I have seen up until now. So that gives me just 3 possible states, right? I have seen either the number of ones is divisible by 3, so that is 0 mod 3, or the number of ones mod 3 is leaves a remainder of 1, or it leaves a remainder of 2. Okay. So the start state over here is going to be what? We have seen nothing. So we have seen 0, 1. So we'll assume that is divisible by 3. So that is 0. Transition function. So I will now directly write the transition function in this form. Okay. So this is, I will denote the state variable over here by Q. Now Q is just the number of ones modulo 3, right? So if I am in Q and I see a 0, then delta of this is what? I have seen a 0 that does not affect my number of ones divisible by 3, right? So this is just going to be Q mod 3, which is Q because Q is already written in mod 3 form. So this is going to remain at Q. And delta of Q on 1, so when I see a 1, I do increase it. So I have to write Q plus 1 modulo 3. Okay. This is my transition function over here. And finally, what is the set of accept states? So we want number of ones is not divisible by 3. So it is either the remainder is 1 or the remainder is 2. So the set of accept states is both 1 and 2. Okay. So now we can, using this, we can write the product DFA. Okay, I will just unzoom this so that we can have both of them in our eyesight. So the product DFA for L1 and L2 would be written as, again we have to give these 5 elements, right? So sigma is 0, 1. The set of states Q is Q1 cross Q2, right? So this is 0, 1 cross 0, 1, 2. So writing this completely, this would be 0, 0, 0, 1, 0, 2, then 1, 0, 1, 1, 1, 2. Okay. The start state is S1, S2. So the start state over here is 0 and over here it is 0. So this is 0, 0. Transition function delta is Q on 0. Delta of Q on 0. What does it go to? It goes to, so Q over here is now Q1, Q2, right? So Q1, Q2. So let's write this. Okay, let's keep this Q1, Q2. So Q1, Q2 on 0. Let's put this equal to, this is equivalent to delta of Q1, Q2 on 0. So this is what? This is what did we write in product construction? It is going to just copy the transition functions of the component DFAs, right? So this is delta 1 Q1, 0 and delta 2 Q2, 0. So what is our delta 1 Q1, 0? It is from here. delta Q0 is Q plus 1 mod 2. So this is what? So this is Q1 plus 1 mod modulo 2, and delta 2 Q2 comma 0 is picked from here. So this is just Q2. Okay, great. And delta of Q comma 1, this is again equivalent to delta of Q1 comma Q2 comma 0, where Q1 is the first component, Q2 is the second component. It will again perform the transition functions of its component DFAs. Oops, this is 1, comma delta 2 Q2 comma 1. So what is this? This is, so delta 1 we will copy from here. So this is just Q. So this remains at Q1, and delta 2 we copy from here. So this is Q2 plus 1 modulo 3. So that's it. Our transition function is given by this thing. Delta of Q0 is Q1 plus 1 mod 2 Q comma Q2. Delta of Q comma 1 is Q1 comma Q2 plus 1 mod 3. Okay. And finally, what do we have to write? We have to write the set of except states, A. So because now this was an AND construction, the set of except states is all. So first of all, it is a set. We will write it in braces. So it is all Q1 comma Q2 such that Q1 belongs over here and Q2 belongs, Q1 belongs to this and Q2 belongs to this, comma, and Q2 belongs to A2. So what is this over here? It is 0, 1 and 0, comma 2. Set of except states. And that's it. That is our product construction. So I hope you have understood that. You can also draw a diagram for this because this is a small DFA. It is not too difficult to draw a diagram, but usually in product constructions, we will restrict ourselves to describing the DFAs because it makes writing the transition functions easier. But yeah, that's it for this this problem. I hope you have understood that, and have a nice day ahead. All the best.